everyone. I'm Zoe from the Royal Belgian Institute in Belgium, and I'm going to talk about my PhD, which is where I study the ecological and genomic drivers of the evolution of wing dimorphism in beetles. And so wing dimorphism in beetles is actually very common. And so here we have a discrete variation where we have individuals with long wings and individuals with short wings. And the individuals with long wings have well-developed flight muscles and they can fly, while the individuals with short wings don't have well-developed flight muscles and they can't fly. So this is a very big difference and a very complex trait. And so we don't see any intermediates, we only see long and short. And we can find both morphs in the same population. And so then the question is like, which ecological drivers are behind this? So we see this actually this is an adaptive strategy to the habitats. So they live in habitats where the habitat quality changes from year to year randomly. And also there's an average difference in habitat quality between the patches. So the difference, the year-to-year difference causes, so that makes them, that's selection for dispersal, while the average differences between the patches select against dispersal. And this is an opposing, those are two opposing pressures, and this results in an equilibrium of short and long wings within the population. I can go on and on about this, but I would like to prefer, I prefer to focus on the genomic part because that's what I'm mainly my research is focusing on. So then the question is, how is it possible that this complex trait has evolved several times? So I mean, this can only, so the requirements for reaching this equilibrium is that from one day to the other, the short allele must have arisen. So there must be a mechanism that causes this quick evolution. And also, so very important for this equilibrium is that this trait is Mendelian. And so what I'm looking at is so which mechanism might be causing this very fast evolution multiple times. And so herefore I focus at Bembidion properans. So this is a species that can be found in Belgium. It's very common. Also it has a large spread in Europe. And so the first thing I need to do is assemble a genome, and then I'm zooming into the region which is linked to the wings. And so I completely want to reconstruct the region for the long wings and the short wings. I want to see whether we see like duplication, inversion, any structural variation which is causing the two different morphs. So the first thing was the assembly of the genome. Herefore we use 10x genomics. We use this because we have very small details and it's actually nice to only need to use one individual. So the genome is estimated on 560 mega base pairs, while our assembled genome resulted in 360 mega base pairs. So we actually assume that and it's also quite fragmented. So it's not an ideal reference genome, but there are also we see a lot of repeats in the genome. So we also assume that a large part is just concatenated, while it's so that's smaller. And so further on, I also use resequencing data of 10 long individuals and 10 short ones, and PacBio data. And so the most classical thing to start with is an FST. So we calculated FST values for the SNPs. And then normally we should start looking at outlier SNPs. So, but we actually don't see like normally you would see like somewhere in the end like some outlier SNPs, and that's like, okay, those are regions which are very diverged between the two morphs. But I don't know, it's just like a small slope. So it's a bit hard to say like when is it an outlier. So then we calculate the theoretical FST if you would have, so for the long ones, so 10 homozygous individuals for the long ones and 10 heterozygous for the short ones. But still, it's a very small amount of SNPs, and if you really look into it, we don't see a clear pattern. And here we are really looking for the right scaffolds. It's not an estimation, we really want to know the region. So we took a different approach where we were looking at the SNP pattern. And so we have two ideas for it. So the first thing is, this region could be assembled as one scaffold. I mean, different scaffolds, but like as one. And so for this region, we should see SNPs where we have like a homozygous long-winged individual, which is recessive. And then we should have for the short ones, a homozygous short-winged and a heterozygous short-winged. I also need to add, so we don't know whether the short-winged individuals are homozygous or heterozygous. So this makes it extra difficult. Then the other hypothesis is that these regions are actually assembled as two different scaffolds because they are so diverged. So here there might be scaffolds in the assembly which only occur for the long allele. So that would be within the long individuals and the short individuals. But then we also have, we could have scaffolds which only occur for the short individuals. And so we started looking at this. And so for the first pattern, we didn't find any matches. It's very surprising. And we're really looking into this, but then I'm gonna talk more about it later. And so then we could start looking for the long allele, but the problem here is that we don't have enough statistical power, because we don't know which individuals are heterozygous, and probably quite some of the short individuals will be heterozygous, so this is not a point where to start. And so then we started to look which scaffolds only occurred within the short individuals. And so luckily, this was, here we had prize. And so we found 12 scaffolds. And so altogether they are 130 kb. And we managed to link them all. So they are all linked through the PacBio data, the 10x data, and then we also have insert libraries of 2 kb. So apparently it was pretty easy to link them all. And here you can see, so this is just a window of 20 kb of the whole scaffold. And so for the short wings, you can really see that there's a nice coverage. Well, for the long wings, there are like some repeats because the genome is full of repeats. But it's very clear that it only occurs within the short winged individuals. So, and then I thought like, okay, let's use this. Maybe this scaffold we can use to like retrace the long wing region, because it might still be somewhere. And so I mapped the short wing region to the remaining part of the genome, hoping that some parts of the short wing region would map somewhere. But apparently we don't see, so here this is the bottom line is the assembled short region. And so we only see like very short, like a max of 2 kb mappings to other scaffolds which are repeats. So we don't find any region in the remains of the genome which is where the short region maps to. So that shows that the short region is unique for the short individuals, which is quite surprising because the short morph is derived. So that makes us still wonder like what's going on there. So the next thing to do is actually we're gonna like now I'm gonna assemble a genome with PacBio, and I'm gonna make 2 different libraries of the long one and the long individual and short individual, because maybe with the assembly because it's a heterozygous individual, it kind of got messed up and it might be like more clear cut. But that we still don't know like what's exactly going on there. But to conclude, so we did find 130 kb region for the short wings. The long wings is still a big question. And so hopefully this will get resolved with the PacBios, and then we would also like to look at the different expressions between the short and the long winged region. And I would like to end by thanking everyone who was involved in this project, and I'm happy to answer any questions or remarks, or someone who has an idea.
I was wondering what efficacy of the smaller examples.
Because the long wings, I mean, it's a very complex trait. So the long wings within the carabids, that's an ancestral trait. I mean, it's a very complex trait. I mean, it involves like, I mean, the forming of the wings, the wing muscles. Yeah.
So it's a kind of loss of function.
Yes. Yeah. You were maybe thinking like, yeah, I mean, a deletion or like often it's a deletion, but yeah, we haven't seen that, so we haven't found that yet.
I think that the short could be like a structural rearrangement, so like inversion or something like that. Have you tried flipping it the other way and trying to map it to get the long?
Yeah, Mimmer does it in both ways.
Okay.
Yes. Yeah. That could be very. Yeah. That's one of the ideas, but it might be in there, but we haven't found the region yet. Yeah.
How much is any flying either more actually?
Excuse me?
How much, if any, flying is either more actually doing?
I'm sorry.
How much do they fly?
Yes, but so it's very important for because of the fluctuations every year of the patch, there's a proportion of the populations that colonizes other populations because of the difference in habitat quality. So it's really important. Yeah, it's a very functional trait.
And the short wings, do they fly at all?
No, they don't fly.